So this will be my second run through of the notes for section 3A, which is a little bit of review from last year as it pertains to infinite series. So the first few slides are review from junior year. And so I will give you guys some time to just take notes, write it down. You can always pause the video to copy down any of these notes if I go too fast. So the first slide talks about arithmetic sequences, and arithmetic just follow linear patterns. So each time you add or subtract the same amount from term to term. So in the first example, you're adding 2. Second example, you are adding 8 over and over. Sorry for the handwriting, it's a little hard to write with a mouse. And the third one, you're subtracting 2.5. So slide 2 was how you find the general term. And so, for example, if I tell you that I have, going back to the first slide here, if I have 1, 3, 5, 7, 9, the first term of the series was a 1. The common difference, in this case, you were adding 2 each time. And so if you want to find the nth term, say, for example, I want to find the 10th term, use this formula, which says take the first term, which is 1, plus the common difference, which is 2, and make sure it is a positive 2 because you are adding, times the quantity n minus 1, but in this case, we know what n is. N is 10. Let's do 10 minus 1. And so the 10th term of the series will be 10 minus 1, which is 9, 9 times 2, which is 18, and we'll get rid of that guy. We don't need him. So 10 minus 1 is 9, 9 times 2 is 18, plus 1 is 19. So the 10th term in the series will be 19. Okay. The third is if you want the sum of a finite series. So again, take the example of 1, 3, 5, 7, 9, and I wanted to add these terms together. Now, if it's a short enough series, you can just go ahead and add 1 plus 3 plus 5 plus 7 plus 9, which would be 4, 9, 16 plus 9 is 25. But let's say it's a longer series, you would not want to add all of them together. So you would use this formula. So in the shortened example here, the sum of the first 5 terms would equal n, which is 5, divided by 2, times the quantity of the first term, which is a1, plus the nth term. So in this case, if you want the sum of the first 5 terms, you want the 5th term here. And we'll kind of scoot through a little bit because you guys should be able to do the math fairly quickly. 1 plus 9 is 10. 10 times 5 is 50. 50 divided by 2 is 25. So the same number we got by adding them. And this is a little review of some of the notation we will use for different Greek letters. So both of these particular values are sigma. This is the uppercase and this is the lowercase. So our uppercase sigma notation we use when we're adding terms of a series. The lowercase is something we learned earlier this year as it pertained to standard deviation. Or if you square it, you've got variance. And so just a quick review of sigma notation and how we use it. Let's start with the bottom. The bottom defines your variable and the starting value of that variable. And then you count up by integer values until you reach the top, which is 5. So this is the last term in the series. So I would equal 1, followed by 2, 3, 4, and 5. So this particular series written out would look like this. And you can go ahead and square the values and add them up, but I'm not really concerned with what the actual value is. I'm more concerned with taking a series written in sigma notation and being able to write out the terms. Same thing here for part B. You've got the sum from 0 to 4 of 2x plus 1. So you start by plugging in x equals 0. 0 times 2 is 0, plus 1 is 1. And then you plug in the number 1. 2 times 1 plus 1 is 3, and you keep going and going. And then you stop at the number 4. 2 times 4 is 8, plus 1 is 9. And again, I don't really care what the sum is. This one, same idea, just a slightly more complicated equation here. And also, do you notice You do not always have to start at 0 or 1. Some series start a little later. This one starts at 2. So the first value you plug in for k in this case is 2, and 2 to the second equals 4. And then jumping into geometric series, this kind of went along the lines of arithmetic from junior year. So geometric series are essentially the same idea as arithmetic, but instead of adding, you are multiplying. So in this case, the common difference is 3/4, because if you look at the first value, 2, and you multiply by 3/4, you get 6/4, which reduces to 3/2. And then if you multiply 3/2 by 3/4, you get 9/8, and so on and so on. And so this particular value, if you continue the series to infinity, written in summation notation form, would look something like this. And then the two other equations that have been on the window for a while are if you want the sum of the first n terms, so a finite series. So if you want the sum of the first 2 terms or 3 terms or 10 terms, you use this formula, where a sub 1 is your first term 2, r is your common difference, which is 3/4, and then you just plug those values in. If you want to find the sum to infinity, so it has to be an infinite geometric series, a couple things have to come into play before you use this formula. First is whatever your r value, let's clear some of the ink. Your r value, which is right here, which is 3/4, must be between 1 and -1. If it is between 1 and -1, your series converges. So if that's true, then you are allowed to use this equation, which gives you the sum to infinity. So if you were to add the infinite terms of this particular series, it would eventually get smaller, or the values would get smaller, and it would approach a particular value. And so in this case, all we need from this equation, you cut that out, and you're left with this part right here. So you plug in the first term, which is 2, over 1 minus r, which is 3/4, and if you simplify, you get 8. So if you were to take your calculator out and do 2 plus 3/2 plus 9/8, and so on, eventually your series would approach 8. Then we start diving into infinite series, and we explored this a little bit last chapter, but we didn't really look at them as series. We were looking at the transition to improper integrals. And so we determined that an improper integral visually was you were looking at a graph and you were essentially finding area under the curve and wanting to know if that particular area modeled finite behavior. Well, another way to look at that is we were really looking to see if this particular equation, which the one we started with was 1 over x, converged. And so if it converged, then we knew it got small enough fast enough. And so a couple series to kind of look at here. First one is a very simple series. And so we're starting at k equals 1, and you're plugging that into k, so you're really not doing anything to it. So the first value is 1. And the second value climb is to 2, and they keep climbing to 3 and 4 and so on, and you continue this all the way out to infinity. Now here, clearly the values are getting larger and larger, so if you add higher and higher values, the series will approach infinity, therefore it diverges. And then similar to the one we did up here, we have something called the harmonic series, and we had not really called it that. But the harmonic series is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And so it's the series where you're plugging in each value of k into the function 1 over k. And we figured out last chapter that 1 over x as an improper integral starting at 1 did not get small enough fast enough. So the area under that particular curve, if you went out to infinity, approached infinity. So it did not model finite behavior. And we're going to find the same thing happens here in this harmonic series, that if you add 1 plus 1/2 plus 1/3 plus 1/4, that this particular series, even though the values that you're adding are getting smaller and smaller and smaller, the series actually diverges, which means this approaches infinity. It never approaches a particular number. I'm going to go ahead and stop for part 1, and I will add part 2 shortly.